So 1-1 is called Parent Functions and Transformations. This entire chapter is just to introduce you to the basic shapes of basic functions and to start describing how they move on a graph. So the very first vocabulary word that you're going to need for this section is a parent function. A parent function. And this is a basic shape in a group or family, which is why it's called a parent function, of graphs. So if we look below, we have a linear function. A linear function is basically a line, okay? Pretty obvious. A quadratic function is basically a U. And we can go on to the other functions, and we'll look at a couple more in a second. But the functions that you see on your paper or on the screen are going to be later in the chapter. But the two that we really want to focus on are actually the linear, the quadratic, and there's one more which is not pictured here. So here are the four main shapes that this particular section is going to talk about. Obviously, we're still going to be focusing mainly on just two of them, but I'm showing you all three just so that if a homework problem arises, you'll know exactly how to treat it. So some basic information, we have our constant and our linear functions, and these two are very similar in the fact that they are just straight lines. If we were to create the function of our constant function, or we were to create the graph of our constant function, we'll need a xy graph. And just a quick note, this k and then that weird symbol and then another weird looking z, this is just saying that the letter k that is currently being used in the function can be any number, any real number. So I'm just putting that out there. It just depends on what the book is saying. Is the book saying that k equals 1? Does it say k equals 2? Does it say k equals -6? Your book will usually tell you. I think in this particular example, we'll do 2, but for now, let's just put any number possible, and then we'll do an XY chart. And when you do an XY chart, you always want to pick -2, -1, 0, 1, and 2. After you pick those as your inputs, if I were to input these particular numbers in, it doesn't actually change anything, and I still end up with an output of 2, or in this, if we were doing the general case, k. So if we had k for everything, then we can establish based off our problem, or by this particular example, that we're going to say k equals 2. So pretend all those k's say 2, so if I were to put my points on my graph, it would be the ordered pair -2, 2, which is here, the ordered pair -1, 2, which is here, the point 0, 2, there, ordered pair 1, 2, there, and then the ordered pair 2, 2. So I have all 5 of my ordered pairs graphed on the coordinate plane, and now that I have those 5 basic ordered pairs or inputs, then I can go ahead and make an assumption about my picture. I can see from the picture it looks like it's going to be a line, and it's just going to be perfectly horizontal. So it's not going to go up, it's not going to go, it's just going to lay flat. So this is going to be my line, and I'll add my arrowheads, and that should be that. The next thing we're going to answer about this is our domain and range information. So remember, the domain is going to be your x values, while your range are your y values. If we look at our graph, we can see that our line extends to the right and to the left, or for the x values on the right and the x values on the left, infinitely. We can also see it very easily on our XY chart, that -2, -1, 0, 1, 2. If I were to get smaller and smaller and smaller with the negative numbers, then it would still have a value of k, or 2. If I were to make it larger with my positive numbers, again, I will still have a value. So the x values are changing, and because of that, we would say that the domain is all real numbers, okay? Then our range does not change at all, okay? So if we were to do a general form, we could say that our range, or our y values, are always equal to k. In this particular example, though, we would say y equals 2 because that is what our example established. So linear is very similar, except now we are involving slope, which is something you guys had from Algebra 1. So first things first, let's create our XY chart. We'll use our most common numbers, and then we are going to plug them into our function. If I plug it in, there is nothing that's adding or subtracting or multiplying or dividing my x. So whatever I plug in is what is going to come out. So if I plug in -2, I'll get -2, and etc. If I put my ordered pairs, the ordered pairs would be -2, 2, -2, -2, -1, -1, 0, 0, 1, 1, and 2, 2. Now I can make my assumption about my line, and I can connect the dots. Once I'm done with that, I can easily see my domain or my x values, again, extend infinitely to the right and to the left. So I would say it is all real numbers. It could be anything. And the same thing occurs for my range as well, all real numbers. All right, and again, we can see this within our XY chart. Even though we stopped at +2, I could have gone even further, and I could continue going forever. And because I can go forever, that's why it's all real numbers. Let me add the S. Okay. So the last two is what we're really going to focus on, is our quadratic and our absolute value. So the first one, quadratic function, you may not have seen before, but if we were to create a XY chart and plug in our most common values, well, if I plug in -2, -2 squared equals 4. And then -1 squared equals 1. 0 squared equals 0. 1 squared equals 1. And then 2 squared equals 4. So putting my ordered pairs, I have -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. This creates my U shape, as I said just a little bit above. So connect those, and I can see that my domain, again, is all real numbers. And my range, it looks like it can extend infinitely upwards, but its lowest value is 0. So I'm going to say, well, y, because range always talks about your y values, so y is greater than or equal to 0. And I know it's equal to because if I plug in 0, it equals 0. Same thing is going to happen for our absolute value. Our absolute value, we plug in our x common inputs, and please remember that when you are doing the absolute value is a distance, so it's always positive. You can't go -6 feet. It's not possible. So when you are plugging in your numbers for this absolute value, it ends up just making all of your inputs positive. So if I plug in -2, that'll give me +2. Same thing for that -1, +1. 0 is already positive, so it just outputs another +1. And then 2. 0, 1, and 2 are all positive. All right? So if I were to put my points, I should get -2, 2, -1, 1, 0, 0, 1, 1, and 2, 2. And now I can see instead of this making a U shape, this actually is going to be a V shape. All right? So again, if I look at my domain or my x values, I could keep on going forever, and I can infinitely get smaller, but I can also infinitely get bigger. So that's every single number. So I would say all real numbers. And then for my range, I have something very similar to the quadratic. It gets bigger and bigger and bigger, but it stops at 0, and it doesn't get any smaller than that. So I would say that y is greater than or equal to 0. So I can have any output as long as it is bigger or equal to 0. Some other vocabulary that you will need to know is the word transformation. A transformation is a general term to describe a change in its size, its shape, its position, or orientation of a graph. So basically, it's just a change of some sort. So I have 3 examples of how the graph changed. I'm going to put our parent function in black, and you can see that the green function became skinnier, and so that transformed. And we'll describe what those transformations are later, but the red one also transformed by getting wider. In the next picture, we have that red, which I'm going to highlight in black. All right, it looks like instead of it getting skinnier or wider, this one is now moving to the right. All right, and then the last one, I'm going to put our parent function in black again. All this one did was it flipped. All of these are types of transformations. We'll get into the specifics with the next vocabulary word, which is going to be translation. A translation is specifically when you move left or right or up or down. It is a transformation that shifts the graph horizontally or vertically, but it does not change its size. So it doesn't become skinnier or wider, and it doesn't change its orientation, which is when it flips upside down. The important thing to know with this is that typically you are going to be given the parent function instead of as a black line, but as a dotted line. So in our bottom left picture, we have an absolute value, and it is a dotted line, and then beneath it, it is a solid line. The dotted line is the parent function. You can consider this your starting point. But the solid line is our transformation, or in this particular case, our translation. So make sure you have this part highlighted, and then we can easily just count from where we started, which is going to be at that origin, that 0, 0, and we can count downwards how many units we moved, and then just explain the direction. So if I were to count, I went down 1 unit, so I would just say this translates down 1 unit. All right, and then we do the same thing for the one to the right. Again, we have our origin. We move 1, 2, 3 to the right, and so that's what we would write. Translates right 3 units. So here are some examples. This says describe the transformation of f of x, or of the function. In example 1.1a, we can see on the left that this is a V shape. So I know that this is going to be an absolute value function. All right, and I can see my starting point is again at the point 0, 0, or the origin, and it should always be so for your functions, except for the constant. The constant is going to be based on whatever the problem tells you. I can just count how many times it moves over to, in this particular case, the right. So it is 1, 2, and that's what I would write. I would say it translates right 2 units. All right, and do the same thing for the next one. To the right, we see example 1.2. Again, the directions are the same. We see it is a line. It might be a little hard to see, but there is a blue dotted line that is completely flat. So I know that this is going to be a constant function. And again, this particular problem starts it down at -2. So I'm going to put that as my starting point. I know it's my starting point because it is a dotted line. And I'm going to count upward, in this case, to the solid line, and how many times that is. 1, 2, 3, 4, 5, 6. All right, so now I can say, well, this particular function translates up 6 units. Here are some more examples. This is example 1.1 and example 1.2. All right, so in 1.1b, on the left-hand side, we see a quadratic function. and we can shorten that function by just saying f of x. All right, we see that our dotted line, again, is our starting point at 0, 0, and I'm going to count how many times it goes downward, and it looks like it is going to be 3 units down. For this case, I'm going to shorten it up a little bit just to save on some space, and I'm just going to say it is down 3 units. All right, to the right, we have a linear function because it's a line. All right, again, starting at 0, 0. We count upwards, 1, 2, 3, 4. All right, so that should be up 4 units. All right, so even if we have more than one type of translation happening, we are just going to tack it on at the end. So in example 1.1c, the bottom left, we see it as a V shape, so we know that's going to be absolute value function. All right, and then I put my starting point at the origin, and I'm going to count to the right 1, 2, 3, 4, 5, okay? But my ending point is not there. It's actually over to the right 5 and then up 1, all right? And so because it does two things, I'm just going to put the two together. I'll say it is to the right 5 units and up 1. The example 1.2c is quadratic because it is a U shape. Same process again. I have my starting point at the origin. I see that it goes up 5 units, and then it goes to the left 1. So I would say up 5, and that's not right. Up 5 and left 1. And this would be my description. So the next specific transformation we'll look at is the reflection. A reflection is going to be a transformation that flips a graph over a line called a line of reflection. And typically this is when you have a negative in front of your function. All right. So if we were to emphasize anything here, it's that you have to have a negative either immediately in front, well, it should always be in front of your x. All right, and so if we were to look at our point or our line of reflection, it's always going to be the line in between our two shapes or our two graphs, right in the middle. So in our picture to the left, it looks like it is on the y-axis, and I'll represent it by a dotted line because technically it's an imaginary line. And then our picture on the right, it happens to be our x-axis. And it's not always going to be like that, but in this particular case, it is. The next specific one is going to be, the next transformation is whenever we have a shrink or a stretch. Now, we can either have a vertical shrink or a horizontal shrink, and we'll explain what that means in the next section, but for now, we'll just focus on the vertical stretch and the vertical shrink. Another name for a shrink is a compression. You can think about it as if you were to have a thing of Play-Doh and you were to put pressure on top of it, it would get bigger and bigger and bigger and become flatter. Okay, so that's the same idea. We're compressing it. And then our stretch, obviously, if you stretch Play-Doh, it gets skinnier and skinnier. So our stretch and our compression, that's what you're looking for, or stretch and shrink, it's fine. I don't care which one you use. The stretch is when it becomes skinnier. It stretches to become skinnier. And this is when you usually are going to have a whole number. Really, it's any number bigger than 1. So it could be 1.1. That's bigger than 1. But typically, they represent it by 2, 3, 4, 17, that fun stuff. So those are the numbers you're looking for in front of your function or in front of x. And then for the shrinking, again, this is when it becomes shorter. And now the number in front of x is going to be a number between 0 and 1, which is typically fractions. Okay, so typically it'll be 1/2, 1/4, 1/5. Those types of numbers are going to identify it as a shrink. So here are some examples of identifying the different transformations that are going to happen. Whenever it comes to linear functions, this is very similar, or it's exactly the same as your Algebra 1 teachings. We can see in 2.1a on the top left, we see it's a linear function. All right, that part hasn't changed. So we are starting at the origin, 0, 0. Again, we are going to find a point on the solid line because that is our true function. So we are going to go over and find a point. If we were to do rise over run, we rose 1 and ran 3. So whenever we're writing the description of our transformation, we would say it has in Algebra 1, we would say it has a slope of 1/3. But now that we're in Algebra 2, we're going to say, okay, is it getting skinnier or is it getting shorter? And we can see it is getting shorter. So we would say this is a vertical shrink and then put the slope, which is 1/3. Okay, same idea with the linear function on the right. Linear function, we're going to go upward to our point. And so we can see now it's getting skinnier, so it is a vertical stretch. And if I were to count it, it would be 5. Technically 5 over 1, but 5 over 1 equals 5. All right, so now let's look at a quadratic. The quadratic one is probably the most complicated just because it has a more complicated function, parent function. So first things first, we can identify it as a quadratic, not a huge deal. We already know that because it is a U shape. But what we're going to do is we're going to find 2 points on, or really 1 point on the solid function, on the solid line. We automatically use the origin and whatever point that we find. So we have that 0, 0. And we have, it looks like it hits at 2, 2. So if I were to put that right here, it'd be 2, 2. Okay. If I want to find how much it stretches or shrinks, I can easily see it shrinking. It's getting shorter, okay? But if I want to easily find it, there's a formula. So I'm going to write it off to the left. It says y over x value over just your x value. Okay, so if I were to find those two values, it would be our -2 and our 2. And I'm going to plug those in. And I'm not going to worry about the signs of it right now because it's not very relevant. So I would say, okay, this is going to be my x, that's going to be my y. I'm going to write down really quick that it is a vertical shrink. And then I'm going to find my value. All right, so it should be 2, that's my y value, over 2, which is my x value, over just my x value, which is 2. And if I were to solve out the numerator, 2 divided by 2 equals 1, over 2. So I could say that this quadratic function has a vertical shrink of 1/2. That's all that happens, and we'll practice more of those later. To the right, we have absolute value function. Oh, and this formula is only for the quadratic function, by the way. All right, so to the right, we have our absolute value function. And we can see that because it goes downward, it is automatically a reflection. And I'm just going to go ahead and figure out if it's going to be a stretch or a shrink. It looks like it gets skinnier, so I can say it's a vertical stretch. And then if I use my slope or my rise over run, I can see that it's actually going to be a vertical stretch of 3. Okay, so these are the descriptions that I would be looking for if you were given a picture and asked to describe the function. So we've done some examples of how to describe the transformation if you see the picture. But what if they don't give you a picture? What if they just give you an equation and they ask you to figure it out? Well, there are some tips and tricks for that. It is called the vertex form, or it could be just the standard form, but particularly we're looking at the vertex form for a quadratic function in particular. The blank in front is whatever number is being multiplied in the very front. Sometimes it's just 1, and if it's just 1, you can ignore it. But if it's anything else, it is in the A position, and it is going to signify we have either a reflection if it has a minus sign or a negative symbol, and A will also tell us if we are stretching or shrinking. Remember, stretching is when A is bigger than 1, so 2, 3, 4, and shrinking is when A is between 0 and 1. The next one we have is our H, and H and K, which I'll give in a second, are going to be our translations, okay? Specifically our translations. So remember, transformation is a change of any sort. Reflection is when you flip. Stretching and shrinking is when you change the size, and then H and K is when you move left, right, up, or down, which is called a translation, okay? So H is going to tell us that it moves left or right. Now, if you notice inside of those parentheses, you have a minus sign, and because you have a minus sign, the important thing to know about this is that it is always going to do the opposite of what you see. Okay, so if you see a -4, okay, you think, okay, it'll have to move to the left 4 because that's where the -4 is, right? But because it is a x minus h, you're going to do the opposite. You're actually going to go to the right. And I'll show you a little bit more in a second. So then the last letter, or the last position, if you will, notice how this last position is not inside of the parentheses or any grouping of any sort, is going to be our K. And K, it tells us if we're moving up or down, and because there is no minus sign, it moves as normal. So in example 3.1, all right, we're going to go through all of these. We have our linear function up first, and I know it's linear because it sort of follows the equation that I gave on the front page of your notes, or maybe page 2, where it says y equals x, okay? And because we have a +4 and it is not within grouping, we would say it is a plus or up 4, okay? And again, I know it's linear because it follows y equals x. So then letter B says x squared. Well, the quadratic equation had an x squared. So because it follows x squared pretty closely, I will say this function is a quadratic. And then I have a -1. Again, not within the grouping, so it has to be the K position. This is going to be down 1. All right? Letter C is a little unorganized, so I'm actually going to switch it based off of the commutative property of addition. And so it will actually say the absolute value of x minus 5. And then again, this one's very obviously a absolute value function because it has the absolute value symbols. And I see we have a -5 within the absolute value symbols. And because it's within our grouping symbols, I'm going to treat it like H, where it goes left or right. And I will do the opposite of what it says. So it says go to -5, which is on the left. But that means, because it is in the H position and I have to do the opposite, that this is actually going to move to the right 5. All right? Example 3.2, now we're going to involve more than one transformation. Letter K is a linear function, and I can see that that -2 is outside of any grouping, so I will say it is down 2. And then I have that 1/2 in front. Now remember, if we have a fraction, that is going to be a shrink. So I would say this is a vertical shrink, and I'll just put by how much, which in this case is 1/2. Letter B, we have a quadratic function. I know it's quadratic because it says to the power of 2. And I can see that it is going to be a vertical stretch of 3. All right. Again, I know it's a vertical stretch of 3 because the 3 is in the A position, and it is a number bigger than 1. The next thing is inside of our grouping symbols. I see a +4. So typically, if I'm moving left or right, and I see a +4, I want to go to the right, but I have to do the opposite. So this is going to be left 4. And then finally, that +1 is in the K position, so it would be up 1. The last function that they give us is n of x. This is going to be an absolute value function. And the first thing that we see is a negative. Now remember, a negative in front is in the A position, so we know it's going to be a reflection. A reflection. All right, and then the next piece we see is a +5. It's inside of the grouping symbol. So instead of going to the right, it's going to be to the left 5. And then finally, down 3. So example 3's direction says after you're done to go ahead and graph the parent function and its function. Or its transformation specifically. So we have our x plus 4 and our 1/2 x minus 2. And we know that these are going to be linear functions. So I'm going to start with example 3.1, that x plus 4. The parent function, again, we've already done it before if you want to just keep reusing those values, but they're going to be these points, and I will draw a dotted line to show that that is the parent function. And then all I'm going to do is I'm going to follow the directions that I wrote in example 3.1. I wrote that it went up 4. So I'm going to start at the origin just because that's what I'm used to, and I'm going to move that point up 4 times. And so that is going to be its new position. And I can do that for each point and get these points like this. Draw my line, and it's going to give me this. So we see that the two lines are parallel. If I wanted to double check my work, I can always do that XY chart that I mentioned before. Use your values that I mentioned at the beginning and plug them into your function. So -2 plus 4 is going to give us 2. -1 plus 4 is going to give us 3. 0 plus 4 is 4, 1 plus 4 is 5, and then 2 plus 4 is 6. And I can see that I have those points here, here, and here, and I can check every single one of them, and they all work. Okay, so it doesn't matter to me which way you do. You should always try one way and maybe check with the other. That's always a good way to approach it. So then 1/2 x minus 2, again, we have the same parent function, so I'm going to go ahead and draw that. All right, I'm going to do the same thing with my vertex. It's going to be down 2, 1, 2. So this is going to be my new point. And now, instead of having a slope of 1, which is a parent function, I am actually going to have a slope of 1/2. So I'm going to rise over run and find my point here. And if I were to go the opposite way, I would find my point there. So now I can connect my dots, and I should get something that looks like this. Again, I can check with my XY chart, plugging in those common values, and I should get -3 for the first one. I'll get a fraction if I plug in -1, so I'm just going to skip it for now. But if I want to double check, I can actually see that -2, -3 is right there, so it did work out. If I plug in 0, I'll get -2, which is right there, and then plug in 2 and I get -1. So I have the ordered pair 2, -1, which is right there. So I have correctly drawn my picture. Obviously it's not super beautiful, but you get the idea. So example 3, letter B's, I went ahead and since they were both quadratic functions, I put their parent function already. And remember, if you want to see what the ordered pairs are for that, just go back to the beginning of your notes. So in example 3.1b, our function is x squared minus 1. So pretty straightforward. We take each point and we just bring it down 1 space. All right, so if I do that, these are my new points. I'm going to connect the dots. And if I wanted to double check it, I know it's not super exact or pretty, but you'll get over it. But if I wanted to double check, I can do that XY chart. Plug in my most common numbers. -2 squared is going to give me that 4 minus 1, which is 3. Plugging in the -1, I should get 0. And then 0 squared minus 1 is -1. And then after that, it starts to repeat because a quadratic function is symmetrical. So I can double check that these points are actually on my graph, and they are. I can see them here, 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 and here. Okay, so I know I did it correctly. The one to the right is a little bit more complicated, but it's okay. Even though it's a little bit more complicated, it's going to be almost as easy. So again, we're starting at our origin, which is 0, 0, and I'm just going to go to the left 4 times, all right, and then I'm going to go up 1, and this is where my origin's going to be. The only other thing that I really have to do is consider that A is making it stretch or vertically stretch by 3. So it's going to get skinnier. So what I can do is from my origin, I can count up 3, move to the left, put a point, and move to the right and put a point. So if I go up 3 to the left, it should be here. Up 3 to the right should be there. And now this is going to be my U shape, okay? Again, let's check with the XY chart, but this time, instead of picking the -2 to +2, I'm going to actually pick the numbers I can see. I can see that it's over -3, -4, and -5. I'm plugging them into my calculator and I get 4 right there, 1 there, and +4 there. So again, I know I did it correctly, and it's not super important that you're being exact whenever you're drawing your picture, but it is super important that you're being exact when you're putting your points down. So again, since the letter C's are both absolute values, I went ahead and put their parent function on here for you. And in the 3.1 example, we see that it's just going to the right 5 times, as we described previously. So we're going to move our vertex to the right 5 times and have a point here. And since it is a absolute value picture, we know it's going to be V-shaped, and we don't see any reflection or stretching or shrinking, so we know it's just going to go by 1s, and so this is just going to be a V shape. Again, let's check our values with the XY chart. And since -2 to +2 are on the chart, I'm just going to go ahead and plug them in. I should get 7, which is right here, and if I plug in -1, that should give me 6, which is right here. Plugging in 0, I should get 5, which is right there. 1 gives me 4, which is right here. And then finally 2 gives me 3, which is right there. So again, I know I did it correctly. I will say at this point that sometimes using our XY chart with -2 to +2 is a good thing, but then sometimes it can be misleading. For example, if I were to just use the XY chart, I might think accidentally that this is going to be just a linear function, because so far it's just been a line. It's not until we get to that vertex when it starts going back upward that we can clearly see it's an X, or not an X, but a V. So the XY chart is very helpful, but don't let that determine if it's going to be a linear function or a quadratic or whatever it may be. So then the last example to the right is going to be 2 or 3 steps really, and so we're going to say, all right, we see that +5, that means it's to the left 5 times and down 3, so it's going to be that point down there. And again, we're just going by 1s, but this time it is reflected, so it's going to be going downward. Okay, and since the -2 to +2 is not really on my picture here, I'm going to shift my X values to where I think they are, where that vertex is, which should be -6, 5, and 4. I'm going to use my calculator, plug it in, and I should get, for -6, a -4, -5 gives me -3, and a -4 gives me -4, which is all on my picture here, which I did correctly. All right, so hopefully this helped you, and if you have any questions, make sure to ask me on your assignment.